Oh my God, Ben. Listen, Ben. I think I can't take it anymore. I'm done. I'm done, man.
No,
Ben, you are.
if you look at
Listen,
it,
Ben. You
we're
seem like a
spinning
really
at
nice
a
guy, but you are
consistent
so
speed.
brainwashed. It's not even funny. It's ridiculous. Okay. Don't get my app. Don't watch the daily videos because it's not going to help. Okay. Every question that you have is answered in there, but you will not see the answer. Don't waste your time. Enjoy your spinning ball. All right. So that picture, you got your P900 and you zoomed in on things that should be 50 feet below the curvature, and there it was. And that's what did it for you. That's kind of what did it for me.
Yes.
Ben.
Can you see that screen?
Yeah, so, well, if you bring that picture back up, can you share that picture again?
Is that sharing now?
No, share it again.
Screen share, and then now I bring it back up. Oh, it's gone again. Beach cutouts. That was my first.
What were you going to say about the picture, Ben? There it is.
Yeah, so if you look at that picture there, there's a couple of things that stood out for me straight up is where that horizon line is on that boat. Yeah, if you're sitting only 300 mil off the water, then that boat, where that horizon line from a straight line perspective should be halfway up the hull of the boat, unless it's a little toy boat. So to me, if anything, that horizon is actually curving up from that 300 mil from the ground.
So you think water curves upwards? Large bodies of water curve upwards?
Yeah, it looks like it's actually curving upwards. So then I did a bit of
Don't you think it would curve downwards on a globe?
Well, that's what it should do. But then when you take into account refraction and everything like that, you look at it, and when you get that close to the water, because of the temperature difference between your water and your air temp, from that close to the water, you can never be accurate to measure anything, because you only need 0.1 of a degree difference over a meter to bring the refraction back up to near level.
So how come refraction doesn't everything bring anything up above level? Why does it refract to level and then stop?
It doesn't. Well, you can see it in this one. It actually does bring it above level. You can see it in this one that it actually does bring it above level. You take any, you look at a lot of photos where it's very close to the water. It's never a real clear picture. Like there's always haze. You can see the shimmer of the heat, and it's never a real clear picture. It's not until you get well and truly above the water level that it actually becomes less distorted. Less distorted.
I'll address all of that. There's plenty of pictures across water where I agree. When you're just above the water surface, there is some. I
suppose what I'm trying to say is you can't use a picture like that to determine if it's flat.
I agree with you.
There's too much variation in it to be able to use something like that to determine that it's flat.
So here is a shot on 1 meter, 1 foot above the water.
Yeah, and that's one. Sorry, I was just going to say that's one that you can see. There's a hell of a lot of distortion in that picture there.
Where's that?
Because those outriggers on those rigs there don't curve like that. They're actually supposed to be straight. So you can see there's a hell of a lot. See, on the left-hand side of that picture, that outrigger, where they have the flare set up, it's that.
So skipping that, I agree. There, you do see distortion. I don't know what this is here, but you can see the surface of the water for dozens of miles beyond the outrigger. So, in your belief, that water is refracting up to the level to eye level, and then it's just staying there, and the water in front of it isn't refracting at all. It's only the problem is we wouldn't be able to see the bottom 59 feet of this thing from this height, according to globe math, but we can see the surface of the water beyond it. I don't care if it's blurry. I don't care, whatever. We can see it behind it. And if you watch the video of this,
but then you get another picture another day, and you can only see half of that back.
Agreed. So it's an optical phenomenon when you're looking at a horizon. It's an optical phenomenon like this. Globers will say that the bottom floors are missing, but these balconies.
What's that one?
What's that?
Oh yeah.
So these balconies are all the same height, but they get compressed that's exactly right. So it's not a physical horizon that we're seeing. Here's something that
it's because of the distortion that. See, and that's why what I'm saying, that you can't rely on that to be able to.
All right, so here, explain this one away with refraction. So this is a viewing spot pretty high up. I forget the actual altitude, but it's looking out over the ocean, and 175 miles away is Mount Canigou. But according to globe math, from this height at that distance, the top of Mount Canigou should be a mile below the horizon. So you would think this is the horizon. But on 2 days a year, when the sun in its journey between the tropics lines up with the viewer and Mount Canigou, all of a sudden you can see Mount Canigou, and the very top here should be a mile below the curvature, but it's not, and it's not refraction.
So how do we know that it's not refraction? Like,
because watch the sun go beyond it, and you'll see that it's blocking the actual sun. So if you believe that
so if we measured, like we go and measure the temperature and everything like that to determine how, because we know refraction exists.
So let me ask you a question. You believe that the sun set and this is already a mile below the curvature?
Well, it can be, depending on how much refraction's is
so
there in that photo.
So I can't argue. I can't fight that. If you believe this is refraction and there's no refraction in front of it, it's just behind it. I don't know what to say.
You can't tell that there's no refraction in front of it. That's the point. See, I suppose what I'm trying to say is that unless, because we know exactly how much light refracts in the atmosphere. We know exactly how much light refracts due to temperature change, to temperature gradient. So what we need to do to be able to, take away any I suppose assumptions and everything like that, we need to have that data available. We need to measure that, so then we can say, this is the temperature gradient that was used. This is what, this is how far away it is. So take that into account, then that will tell you, say, this refraction amount was calculated to be, this is the amount of fraction that should be in this photo, and then look at it and say no.
What determines the amount of refraction?
So
temperature, humidity,
gradient.
Okay.
Humidity.
So let me interrupt. As the temperature changes, the refraction should change also.
Yes,
I agree. Okay, so there's we can let me talk. We can look across Lake Michigan and see Chicago 50 miles away, where the tops of those buildings should be below the curvature. And they say it's a mirage, that it's refraction, but it's perfect. It's clear, crisp. So we did a time lapse of Chicago for 24 hours with all different temperatures, humidity, day, night, and the buildings never moved an inch. They stayed perfectly the same. Now, if they were refracted and we're seeing a mirage, then viewing it from different areas would change it. So we then got in a boat, put a camera on it, and drove 50 miles across the lake, and the buildings never moved. They always stayed there. If it was refraction, if it was a mirage, it would have changed. It didn't, right? That shows that we're actually seeing what we see and not making up stories about a mirage.
Yeah, but how do we know that there was no refraction involved there?
Well, because the boat went across the lake and nothing changed. We just got closer and closer to the buildings. And then we also went from daytime to nighttime, which there's definite temperature changes, probably a 20-degree temperature change, humidity change, and they never moved at all. There was no expansion. Now, if you want to see what refraction looks like due to temperature, I will show you what that looks like, and it looks nothing like what we show. Take me a second to find it, but as soon as I do. So go ahead, continue.
Yeah, but refraction is a temperature gradient, not just a temperature, change in temperature.
Well, yeah, but this is a bay, no tides, and just over the course of a couple of hours, you see the beach disappear, you see the buildings disappear. Okay, this is not what we're seeing. But if I got on a boat and drove across, it would change. But we see the same buildings when we did that. The building sizes never changed other than getting bigger because we're getting closer. This is not curvature. This is an optical thing. Optics can block some things, but they can't bring things back into view. Something that's behind a physical curve is gone. You can't bring it back.
Yeah, you can bring it back, but if you bend light down, that will bring it back.
Well, how are you going to bend light down and bring it back in a perfectly clear image? Now, you can't.
Yeah, you can. Because of the temperature gradient and your pressure gradient. See, you understand what the laws of refraction are?
I do.
How refraction works. So,
but it doesn't look like what we see.
It's the change of it's the bending of light through a medium.
Yeah.
So, and when you get a different pressure gradients, say you look into water from an angle, and you can see the refraction as it goes through the water, and it bends it down a long way. And the reason why it bends it down is because because you got the different pressure, different density gradients.
But we're not looking.
The density of water is a lot. Water's a lot denser than air, so that's why you can really see the change in angle of the light.
Can you explain what's happening here?
Yeah, that one's actually a cloud in. I read up about this one. It's actually a cloud that sits in front of the boat.
No, there's no cloud.
It's a low-level cloud. Happens very regularly, and that it also happens.
Well, that's a nice story. I'm glad you didn't fall for the refraction thing, but that's just a boat sitting on the water. There's no cloud. The horizon's behind the boat. It's just smooth water versus wind-swept water. So.
Yeah.
So again, you can make up all these stories about refraction. Yes, refraction can bend light down a little bit, but it can't lift a building up from behind the curvature. Flatter globers will say, there's no boat on the horizon here because it's behind the curvature. But as I zoom in and open up that viewing angle, all of a sudden you can see there is a boat there. And when I zoom all the way in on this boat, I'll zoom all the way in, and you'll see the whole side of the boat. And then the boat's not moving. I'm just zooming out, and just like the boat's going away, and the boat disappears from the bottom up. And that's due to angular resolution limits of our eyes. It has to do with these little waves blocking. Okay, because the waves in the foreground are bigger because they look bigger and they're hiding something smaller in the background. Just like my hand goes away, it gets smaller, and just my finger here can block my whole hand.
Yeah. So that one that you've got there, that boat doesn't go down behind the horizon. I've zoomed in. Yeah, as
the
you
hull is
zoomed out
missing.
there,
The hull is gone.
I zoomed in there to that boat, and it stayed exactly the same amount above the horizon until you couldn't see that boat physically due to the pixels.
Am I looking at a mirage because that boat should be behind the curvature of the Earth?
No, that's just normal refraction.
So it's refracting up. So I'm zooming in on a refracted image.
Yep.
All right. There's no helping you.
Your eyes see the light. So if your light beams down, then whatever you see will look straight. All right. It's hard to explain, but
all right. Let's move away from this because we're never going to agree. We're never going to agree.
What's over that curve? Hey?
We're never going to agree. So let's move on to another topic.
I've got just a couple of questions, and one, well, for a start, timeanddate.com. You aware of that?
Yeah.
Yeah. Why is it extremely accurate at predicting anything anywhere? Yeah.
It's pretty accurate. Yeah. It's just taking the light images and wrapping it around a globe. You can do it. It works perfectly.
So, but then you take, it gives you sunrise, sunset angles and everything like that throughout the day.
Yeah.
You map them out on a, yeah,
I know where you're going with this. You're going to say that you map them out and they don't point towards the sun, but if you put them on a ball, they're all parallel, right?
Yeah, exactly.
You're watching a lot of troll. You're watching a lot of troll videos. So the sun that we see is small and close, but it's not a physical object. We all see it in a different place. If you and I were standing on the street,
so that's
my point.
Yeah. Okay. Sorry.
If you and I were 50 yards apart outside and we're looking at a giant mirror and the sun was setting behind us, and we sent a third person up to the mirror and I said, all right, draw a circle right there with a Sharpie. That's where I see the sun. They draw a circle for you 50 yards away. We're both seeing the sun in a different position. So you can't, we've done videos with amazing math, amazing experiments showing that the sun is not a physical object. The more people you have to triangulate the sun or the moon, the farther off it gets, when actually the more people you have, the closer your calculation should be on its location, but it gets farther and farther off. And that's because we're not looking at a physical object. It's a projection into the Earth system. Again, you don't need to look up at the ceiling. We don't need to go look up at the ceiling to look at the lights to figure out the shape of the floor, because that's, when you look up in the sky, the optics of the sky are no way to prove the shape of the Earth, because you don't know what you're looking at. You don't know what direction things are going in. You don't know anything.
Yeah, but it's just amazing how it fits perfectly to being a globe with the light source a long way away. Everything fits absolutely perfect. So how can you believe that on a flat plane that it doesn't fit perfectly and you can't get it to fit perfectly? So why?
It actually does fit perfectly. So
how does it fit perfectly then?
So for one, on your globe model, you believe that all the light rays are coming in straight and parallel, but these are just refracted, right? Or whatever.
No. That's just your viewing angle, those.
So those are parallel rays. They're all coming in parallel?
If you get further away and up at the cloud height, they will look parallel.
No, not true at all. We've got videos from airplanes. They're not parallel. And as you move up, your view of where the sun is moves up also, because It's it's not 93 million miles away. But if you look at Aristophanes with his experiment with his sticks and shadows, there's no shadow. There's a shadow with his buddy 500 miles away. They do some math and they figure out the sphericity of this ball, right? Well, one, that's a made up experiment. It never happened. Aristophanes was never mentioned in any books. What?
How do we know that never happened?
Because don't you think that would make him pretty damn famous? And the experiment was never mentioned in any books until the mid 1900s. So to me, that sounds a little made up to me. But even if he did do it, it doesn't matter. With a small local sun, no shadow, do the same math, and you can figure out the sphericity of this flat plane. Okay, we don't live on a math equation. Math can explain whatever you want it to explain, right? So it doesn't prove either.
So so we can use, maths explains everything, and that's the problem that I got. Maths will predict everything that
Name something that math has predicted on the Earth. I don't know what's going on with my camera here.
It looks all right from here.
I'm getting you
a little bit fuzzy.
Yeah, super fuzzy.
But like
Can I ask a question?
Yep.
We just had Aristophanes' example there on a globe, and Dave's shown it on a flat Earth. Math can support both.
Yeah, can you name some math that supported anything for the globe?
Yeah, that experiment right there.
Well,
the math for that, you can do that, and I've done this. I used I used the just doing from sunrise to sunset here, getting the angles of the sun, and from where they are, at 90 from the surface of the ground. You can do the same thing from in the morning and the afternoon, and then map that out, and it fits a globe perfectly to having the rays parallel. But when you go to try and, because I tried to work out how high the sun is, and you get from 50 miles high to 4,000 miles high. So, but when you put it, that was put onto a flat plane, but as soon as you put it onto a ball, that all the view becomes parallel to
but see, you're assuming that the Earth is a ball. You're assuming that the sun rays are coming in parallel, and you can make up a great. These guys, these are troll videos that have captured your mind. That they're showing you something. It works on both. This experiment right here, this says that this floor is in your world is spherical, but this floor is flat. There's no shadow, and there's a shadow. Okay. That's exact. This is a flat floor. It's not a spherical floor.
And that's that there. Those what are they? I can't
Just bottles.
See. Bottles. Yeah. So that there explains your and they're sitting parallel. You said.
I'm showing you that one of their parallel. One of them has no shadow, and one of them has a shadow because the light is above this one, just like this. No shadow, shadow. You can do math that says this is a sphere, but it's not a sphere. It's flat. You're assuming light rays are coming in parallel, but they're not. No one's ever seen light rays come in parallel. Why would Aristophanes ever think that? Do you know how they figured how far? Do you know how far away the sun is in the heliocentric model?
So just going back to those light rays there for a second. So you get two parallel laser beams that are parallel, absolutely parallel. Then you take a photo looking towards those, towards the source. They will look exactly like that, like those light rays.
Right,
there.
I understand. Perspective makes parallel lines. It can,
and that's exactly the same as what you're looking at in this photo.
Yeah, I don't think so. I mean, we could argue that all day, but you won't see it. You know,
Yeah.
is this sun? How far away is the sun? Do you know how far away the sun is in the heliocentric model?
No, 93
million miles away. Very
million
good.
miles away.
All right.
Yeah.
Does this look like it's 93 million miles away, giving us a little hot spot here on the Earth? You know, does this look 93 million miles away?
So how do we know that that's a hot spot? These are the questions. We're just assuming that that's the hot spot.
Well, we can see the sun.
That could be just the reflection off the clouds. It could be anything. We don't. That's what I say. There's a lot of assumptions getting made here, but nothing is actually proven as fact. You know, everything's just assumptions.
It's not really an assumption. That's what I tried to explain to you, Ben. If you grabbed a big torch and stuck it up at the roof, it would light up the whole floor. And if you started bringing that torch lower and lower and lower, forget about a hot spot as in measuring temperature. Look at the spot that's lighting up the most underneath it. Now, a distant sun wouldn't light it up, but a close sun is going to leave a brighter area. Forget about temperature. It's going to leave a witness mark that that's where the light's coming from. That's its closest area. That's what I was trying to explain.
Yeah, but that's not what's happening there, but.
All right. So again, this is something that we're never going to agree upon, and they're never going to be able to prove it. So let's go with something that we can actually explain scientifically. How do you think seasons happen on a globe, Earth?
Well, that's due to the tilt of the.
Very good. Very
tilt
good.
of the Earth.
So here we have the Earth. Here we have the Earth, right?
Yep.
And the northern hemisphere is on the top. Southern hemisphere, here you are down under, you're over here, there you are, right?
Yep.
And when the top is tilted towards the sun, we have more direct rays and it's more concentrated light.
Yes.
Okay. And when we're tilted away, the light is spreading over a bigger area. And that tilt, you know what that tilt is? 23.4 degrees.
Yeah, yes.
Okay, no problem. You don't need to know the actual numbers. So that little tilt, that 23.4 degree tilt goes from, I live in Connecticut in the Northeast here. In the summer, it's 90, 100 degrees Fahrenheit. We're sweating our butts off. And in the winter, everything freezes and we have snow. Okay.
Yep.
And that's just because of that tilt away from the sun. Did you know that in our winter, the northern winter, we're closer to the sun, 3.5 million miles away closer than we are in our summer where we're farther away. So it's really the distance, that 3.5 million miles.
Yeah, it's
only a couple percent.
Less than 0.5%.
It's not less than 0.5%. It's like 3%, but that's fine. But that's all right. It's still, I'll give it to you, insignificant. We'll say it's insignificant. Okay. So can I tilt this ball this way? Right? I can tilt it this way, right?
Well, I suppose you can. Yeah.
Can I tilt it this way? You can tilt the ball any direction you want.
Yeah.
Okay. So in the summer here, during our summer solstice, I can go down to the beach, and when the sun appears on the horizon, at the most severe tilt, it is tilted. So if I'm here, the sun is over here. The most severe tilt. Okay. And I could watch the sun appear on the horizon, and I could feel the heat blasting on my face. And within a couple of minutes, it's hot, right? And that sun, I can feel blasting on my face. Then December 21st, during our winter, during solar noon, not when the sun is all the way over here, when the sun is high up in the sky, as high as it will be, giving us much more direct rays. And we're 300 million miles closer, 3.5 million miles closer, not 300 million, sorry, 3.5 million miles closer. I can look up at the sun and I can't even feel the heat on my face. Can you explain that?
Yeah. Is it the same? So you're saying that it's the same angle?
No, I'm saying let me explain again, just so you have the idea. At noon, whenever the sun is the highest point on December 21st, up in the sky, I can measure the angle. I'd say it's 50 degrees. It's not as high as it gets in the summer. It's 50 degrees up in the air. I can look at the sun and I can't even feel the heat on my face. And it's supposedly closer, but we'll just wipe that out because that doesn't matter. Then at sunrise in June, when the sun is at the most severe. Any farther, it would be below the horizon. The most severe angle, I can feel the heat hitting me immediately. How do you explain that?
Well, all I can say is going from the same scenario here, but it doesn't. Well, we don't get snow here or anything like that. But
there's a reason you don't.
But I don't know why up there, it doesn't feel as hot in the middle of the day as what it does first thing in the morning here, morning in the middle of summer. But here,
you can do the same thing.
I don't. In the morning in the middle of summer, it's hot, but even in the middle of winter, you look at it in the middle of the day, and it still burns you. It doesn't.
Yeah, it's still warm. You know why? Because you are in the tropics. Let me show you how seasons work. Before I show you how seasons work,
I'm below the tropics, but yeah.
Well, you're right. Australia is right on the Tropic of Capricorn. Okay, so
the northern
explain
half
that.
of Australia
is. Here's an experiment. Imagine it's cold. You're out. You're up north, and it's snow. There's snow on the ground, and the two of you go out and get beach chairs, and you sit down in the snow, 15 feet apart. So you're sitting there. It's cold. Okay, you're both freezing. You're both freezing. Then I come over to you, Ben, and I hold I got a nice big heat lamp, and I hold it 10 feet over your head. It's directly above you, and you can feel that heat on your body, right? Okay, that's your summer sun. Tristan, right? Tristan?
I'm freezing,
Yeah. Tristan's freezing. He sees the sun lower, it's lower in the sky because it's farther away from him. Just like in my northern winter, the sun is farther away. It's out south. It's lower. He's freezing. Then if I move that lamp over to Tristan, it's higher in the sky for him. And now you're freezing because you're away and your sun is lower in the sky. That's how the seasons work. Let me show you on a map. Okay.
We've had some good debates, Dave. Don't you worry. Ben and I have just about used every letter in the alphabet 7,000 times.
Yeah.
Back and forward. Email.
Flat Earth isn't for everybody, and some people are just very, very deep, and they won't.
So have we got the maths for that?
Yeah. Hold on, I'm going to show you. I'll go over this line.
We got to get you to get the app. That's what you got to get, Ben.
Nah, I don't think he needs the app. All right, so
I love the app.
All right, so here's how seasons work. All right, the sun goes around every 24 hours. It's the hour hand of the clock, and it's not on the hour hand right now because we're observing daylight savings time here. They're lying to us about the time. It's really an hour earlier than they're telling us. So if I speed it up, the sun actually laps the moon once every 28 days. So the moon's phase and the positions keep track of the weeks and the months. The sun keeps track of the hours and the days, right? So, and then I'll just show you quickly. The stars circle around just slightly faster than the sun, and they only lap the sun once a year. So right now, the sun is in this zodiac. Next month, it'll hang out here. The next month, it'll be here in, this is the Tropic of Cancer, and so until it laps the sun once.
Yeah.
So if you look at this inner yellow line, this is the Tropic of Cancer. June 21st, the sun is over there. So if I jump forward to June, here we are. It's over the Tropic of Cancer. We're having our summer. This is everybody in here is having their summer. You're having your winter because the sun is far away. Here is Miami. And Miami, it's very hot in Miami. I'm up here in Connecticut. It's not as hot, but it's still hot. And that's because the sun is very close to us. It comes around, it's over our head like that heat lamp, heating us, radiating heat, warming up the earth. And the reason it doesn't get freezing at night is because the earth holds that radiation and releases it. And every day it keeps charging the earth more and more. So right now, I'm just showing you it's coming around to where I am. Wherever the sun is, it's noon, right? 12 noon in Miami, Florida. Boom, it's hot. Boom, it's hot in Mexico because the sun is above them. You're freezing, or not freezing, because you're right here. Everything in between these lines is always pretty warm. Okay. So if you're in southern Australia, it's a little colder because like Connecticut and Florida, the difference between Connecticut and Florida is, southern Australia. But if I jump the sun 6 months forward, boom, it's right over Australia and you have your summer. The sun is higher in the sky. It's over your head. It has nothing to do with the tilt. If the earth was a spinning ball, every single day at sunrise, it would be freezing, but it's not. And we could feel the heat of the sun.
No, it wouldn't be
Seasons
freezing
prove
because you've
the
got
flat
your
earth.
atmosphere, which holds the temperature in.
Say again?
Actually, just freeze it just there.
I
clock.
can't freeze it. I can stop the clock,
right.
but the sun will move.
Yeah.
What do you want?
What this is another thing that I find very hard to work out is apparently we can only see the sun for a certain distance, and that's how it fades out. Is that right?
Yeah. Well, it fades out for two reasons, and I'm happy to show you.
Yeah. So
Guess what, Dave?
So we'll just assume that. So if you have a look on that picture there, on your clock, sorry, how does the sun shine a lot further down south than what it does? See how it shines, nearly the whole width of the earth.
Yeah,
the sun is.
It wraps around more than half of the ball when it's out here.
Yeah.
When I move it back in, I'll explain why.
That?
I'll
we
explain
can only
why.
see it for a certain.
So if I move it in, you'll see that it actually reverts. There's more darkness than there is light, okay? And the reason for that is because when you bring the sun out towards New Zealand, it's fluorescing the dome more and it wraps around. And we can do experiments with a light inside of a dome, and you bring the light and it wraps around the dome more. And we have tons of videos in the app.
To do that, and I can't get it to work.
Well, no, it actually works perfectly. It actually works 100% perfectly. Here's what doesn't work. On a ball Earth, we in Alaska, we have flat earthers that have verified it. There's tons of videos of the 24-hour sun. When the sun is here, we're over the Tropic of Cancer. This is Alaska here, and it's never far enough away from Alaska to set. Alaska stays in the daylight for weeks at a time, right? The sun never sets. If the earth was a ball, 6 months later, when the sun is over the Tropic of Capricorn, there should be 24 hours of sunlight in Antarctica, but there's not. There's only 4 fake.
But there is.
No, there isn't. There's 4. No, there isn't. There's 4 fake video. There's 4 fake. Listen, I've been down this road 100 times. Send me the video of the 24-hour sun. There isn't one.
Oh, I don't have a video. I'm just going on one of my mates that did a stint down there for the summer.
Yes, it's light. It's light for 24 hours, but it's not sunlight. There's a difference between sunlight and daylight. Sunlight is when you can see the sun. Yeah, daylight is just the sky being lit.
See the sun for 24 hours. So
no, they can't see the sun for 24 hours. Nobody's ever done it.
I'll confirm that. I'll ask him whether it was just whether it was daylight or whether it was.
So we have all of the webcam footage from Antarctica, and we watch the time lapse, and every single day they cut out 8 hours. Boom, 8 hours cut out, 8 hours cut out, and that's when there's supposed to be 24 hours of sunlight, but there's not. There's not.
Yeah,
because the sun, the way it works is in the Arctic. If you're in the Arctic, the sun is arcing around you. And if you're in the Antarctic, the sun is antarcing away from you. Okay? The Antarctic and the Arctic. The sun arcs around you and it antarcs away from you.
Yeah.
So let's talk about the sun, the reason that you can't see the sun. You want to?
I still find that very hard to believe that that's how the sun operates when we got no way that we can measure it to prove it that that's what it does. We're only just
what are you saying that it does? What are you saying that it does?
What do you mean? What am I saying that it does?
You're saying it's hard to believe what?
I don't understand how it wraps around. Yeah, we're saying it's all good and well to say it wraps around there due to the reflection off the dome and that, but there's no way that we can calculate. There's no angles that we can use off an inside of a dome that will allow the light to go all the way around it.
You're just saying that you haven't seen the experiments where we bring a light inside a dome and it wraps around. And it mimics the same light that time and date shows us. It mimics the same thing. I could pull up a video, but I'd rather you do it on your own time.
Yeah.
You're laughing, but
Yeah,
I mean,
well-
it mimics the time and date, the exact shapes that time and date is. We can
Yeah.
take a glass dome and put a light over it, and it'll light up part. Then we move the light closer to the center, closer to the side, and it mimics the same thing the time and date is showing us. Is that a coincidence?
That's a video that I haven't seen yet. So if you've got a link to it, can you send it
It's
to
in
us?
the app. It's where it's what about the 24-hour? It's under what about the 24-hour sun?
I'll look it up.
Yeah, it's all there. So you have a hard time believing that the sun, how we stop seeing the sun, how the sun sets, right?
Mm. So I suppose what the biggest issue that I've got with all this,
Besides the seasons not working on a ball.
the seasons work perfectly on board.
You haven't proved that yet. You haven't told us.
How do you explain? How do you explain? I can feel the heat at the most severe angle when the sun's farther away, and I can't feel the heat when the sun's at a more direct angle and it's closer. How do you explain that?
Well,
let me give you a hint. You
I
can't
don't
explain
know.
it.
I haven't been up there to have a look at it. So no, I can't explain it. But
it is similar.
I can just go for what from what I've seen down here, and
same.
yeah,
it's still the same as what Dave's saying.
Hey,
it's still the same as what Dave's saying.
Yeah. If you believe in the tilted model, the temperature should vary massively between noon and sunset or sun.
Really.
Absolutely. 100%.
The temperature should vary a lot more with a local sun than what it will with something further away, because you radiate radiant heat.
It does. It does. It's hot over Miami. It's not as hot here. It's freezing in Australia in June.
Yeah, your radiant heat difference. Yeah, it's from one spot to another spot, it's 4 times the amount of heat, which means that in the middle of summer at the equator, say 50 degrees, and this is where if we where we knew, because we don't know how high the sun is.
I'll agree with that.
Then it makes it very hard to basically to prove anything if we can't determine how high something is.
How do you explain the example that I gave you? At sunrise, I can feel the heat, and at noon in December, I can't feel the heat. And to make it worse, in December, the sun is millions of miles closer. I can't feel the heat, okay, versus the most severe angle. That there, if you honestly look at it, disproves the tilt theory 100%. There's no argument.
Well, it does.
There's no argument.
Because, you've got other factors besides the angle and that in it. Like you've got, your atmospheric temperature and everything like that.
So wait a minute. So again, at sunrise, I'm going through the most amount of atmosphere, the most severe angle with a farther distant sun. I can feel the heat. I'm going through less atmosphere, a more direct angle. When I'm looking at the sun, let's say I'm looking hundreds of miles across the earth, thousands, whatever. It's going through all of that atmosphere. When the sun is high, it's only going through a little skinny atmosphere. It's going and it's coming directly on me. Can't feel the heat, and it's closer.
But it's not it's not the amount of atmosphere that it goes through. It's just the angle that it hits you from.
So the more direct angle, closer sun, no heat. Most severe angle, distant sun, tons of heat. Explain that.
Well,
say this. I can't explain it.
I can't explain that.
Okay, thank you. I can. Earth is flat, sun is close.
But that doesn't explain that the Earth is flat, but.
Ben, can I ask you a question just off topic? We don't have to go there. Do you believe we went to the moon?
That's debatable.
Debatable.
Mm. So, and the reasoning why it's debatable whether we went to the moon or not is because at the time it was who had the I suppose it was a how do you put it?
Who could make up the biggest lie, bullshit story?
Well, not necessarily. It's I suppose a show of strength. Yeah, it was a big fight between the Russians and the US.
Cool story, bro.
And if we can prove that we went to the moon, it means we got better technology than you have, and all
Cool
that sort
story.
of stuff.
Cool story,
Whether it actually happened or not, no idea.
That's the question.
Yeah. I mean, I could show you that we didn't go, but I don't know, how much you can take. So do you want to see how the sun sets? You want to see why we see a sunset and why we don't see the light anymore?
Yeah.
All right.
Okay.
So have you ever been out on a day where there's a deck of cumulus clouds, spread out clouds, and you can kind of see they're sitting there on a deck, and the ones over your head are, let's say, 5,000 feet high, whatever there is. And then if you look just 20, 30 miles away, those ones that are at the same cloud deck level are merged with the horizon just due to perspective. You zoom in, you could open that up again, but they basically look like they touch the horizon. You're looking at those clouds that are 30 miles away. They look like they're at eye level, but that's just due to perspective. You with me?
Yeah.
Okay. So those clouds look like they're sloping downwards, and they create...
And they also look like they're getting smaller too.
Correct. So we're not talking about that. And then where they merge with the horizon, that's just infinite amount of clouds and atmosphere, and it becomes opaque, and it looks like a horizon. It looks like it's eye level, but it's not, right? And this is how it works. So here's my flat Earth counter, and I have a level line when I'm viewing it from a celestial point of view, from up in the air. And I'm going over, this could either be mountains, this could be the cloud deck, whatever, but I'm over it, and I'm just going beyond it in a level path. Now I have another camera on the other end of the table that's looking up from a terrestrial point of view. This is how we would see this. Now, if I showed you this first, I'd say, is this line level or is it going down? You would say it's going down. And it would look like that the sun is going below this cloud deck or mountains or whatever that look like they're at eye level. They're just going beyond it. Zoom in a little tighter. Look at this line. There's no way you would believe this is a level line, but this is a level line, and it's just going beyond. This, again, is at eye level. It's merged into our horizon. So the sun, this is a real sunset. You would think it's going to go below the horizon here, but it's not. It's going behind the atmospheric deck of opacity. And if you viewed this without zooming in on it, you don't see this difference in space here. It merges together, and it looks like the sun is just going below the horizon, but it's literally just going beyond the deck of opacity. The sun is up in the air, so it goes beyond, and it looks like it's setting, but it's not. Rising, setting. Okay? It's all due to perspective.
So if it's due to perspective, then why does it not get smaller? Why does it
very good question. Very good question. And it does get smaller. So it all depends on when. Hold on. It all depends on where and when you're seeing the sun and what the atmospheric conditions. As it's getting smaller, it's getting magnified also. But there's certain times, certain places, this is in the high plains of Africa, where this is super sped up. The sun doesn't go down. It just goes away, getting smaller and smaller until it goes beyond the atmospheric deck of opacity. This happens on very, very clear days. Now, here's another one where I'm watching the sun. The sun was high up in the sky. This was my drone. And the sun was going down. In 5 minutes, it went from up there to here. And if the earth was spinning, it would just keep on going. But it didn't. It came here and it stopped. And I filmed it for 10 more minutes. It should be going way down, but it stopped. It just sat here. This is sped up 2,500%, I think. And it just sat here. And then all of a sudden, it disappeared into the thickness of the atmosphere. This is on a super clear day. Here it is again. It just It doesn't drop below this apparent horizon. This isn't a real horizon. It just stops and it sits there. Now, my friends down at the beach, they said they saw the sunset from the bottom up 10 minutes earlier. I'm still watching the sun with my drone.
Yeah, it's interesting that you say that. Because where I live in Toowoomba there, we're on top of a mountain, and we look down towards Brisbane, which is at sea level there. And I've never seen the sun do that. And I've watched thousands of sunrises.
Unless you're looking not over water from an elevated position where it's 32 degrees, so there's no humidity in the air, and it's a perfectly clear day, you're never going to see it.
Dave, I've done exactly the same thing. Can I share my screen?
Yeah, go ahead.
Okay, I've done exactly the same thing, and you pushed me out to the beach. And I went out in the morning early with my dad, and I've done this about 4 times. And I have actually filmed the sunrise because everybody told me it actually popped up over the horizon. So I wanted to see whether you were lying, Dave, or whether they were lying. And this is what brought me to it. Now you can actually see the sun appears above the horizon.
Yeah.
You actually look.
Very good. You got a sun fade in, man. That's really hard to get because you never know if it's going to be clear enough. And there it is. The sun fades in.
Fades in above the horizon. I've done this 4 times now. 3 times it faded in, and 1 time it popped up.
That's awesome.
And that's I had to do it for myself. I didn't want to, no offense.
There's a few things that we're missing here in this photo. See how it's really squashed? To me, that says there's a lot of refraction there. That's actually, I can't remember what it's called, where it squashes it all together.
Here, Tristan, let me stop sharing that. So let me ask a question. Explain this one to me. Explain this.
I love this, Dave. Love it.
All right, explain. Hold on. Don't talk so it stays on this big screen. So explain that. You have 2 choices: refraction or gravity.
What are we looking at here?
You're looking at the sun in between the clouds. Clouds in front of it, clouds above it, clouds below it, clouds behind it. Don't try to explain it because I'm not going to try to explain it either. Okay?
Yeah, I've got my theory on that one there, but
I'd love to hear it.
So let me ask a question. Are these 2 tables the same size? Are these 2 tables the same size and same shape?
No.
Yes, they are. They're exactly the same size and exactly the same shape. So don't trust something that you can't go measure, right? You can't look up in the sky.
Yeah, that's the big thing here is we can't measure any of this. So how can we trust it when we can't measure
anything in space?
We can measure everything on a globe. Everything we can measure.
We can see
not
too far.
Just one way.
And you say refraction.
Multiple ways.
We can see too far. You say refraction, right?
Yeah.
You're
so what we. And no one has been able to prove that no, it's not refraction. They just say, no, it can't be refraction. No one has been able to prove that it's not. And this is where...
Yes, we have. You just don't accept the proof. We've time-lapsed it for 24 hours, day and night, no change. We've driven on a boat to show you that it doesn't change, but you don't accept that. I don't know what else I can do. I mean, we're done there.
No, well... Supply the maths to go with it, and everyone will accept it because
how do we figure out how do we know how far the sun is?
Well, that's.
Do you know how they came up with 93 million miles?
To figure it out on a flat Earth, but
wait, no. I'm asking you in the globe Earth model. How did we come up with 93 million miles?
Trigonometry.
So what was the actual trigonometry? What did they use?
So first First, we determined. First, we determined that the Earth was round.
How did they do that? How did they come up with the radius? How did they come up with the radius of the Earth?
Well, there's multiple ways.
Give me one.
So there's the Eratosthenes or whatever his name is.
Eratosthenes, I showed you that works perfectly on a flat Earth. So take that off the table. How did they come up with R?
Okay, so if it works perfectly on a flat Earth, then we should be able to take any 2 points away, or 3 or 4 points away from the sun, and we'll get exactly the same height if it works on a flat Earth.
Wait, explain that. Explain, how do you get the height of the sun?
Just to make it easy, you got the sun directly over the equator, so you know it's at 90 degrees from the ground, from the surface.
Okay.
We know that at the North Pole it is on the right on the horizon. So you can say, for argument's sake, say the angle's about 2 degrees. So then you can work out, the distance from the equator to the North Pole.
And that doesn't come out to 93 million miles, by the way.
No, it comes out to 50 miles.
Yeah, I'm down with that. I'm down with that.
On a flat Earth.
Yeah, okay.
But then
let me tell you how they came up with the 93 million miles, okay?
So,
you want to know?
Yeah, I'm just explaining it.
Okay.
So doing this, say we assume that the Earth is flat. The sun's at the equator, 90 degrees, directly above you, middle of the day. At the North Pole, it's on the horizon, we'll say about 2 degrees. We know exactly the distance between the equator and the horizon, and the North Pole, sorry. So you can calculate the height of the sun, which works out to be about 50 miles.
Okay,
so
I'm with you. Thank you. The Earth is flat. The sun is 50 miles overhead.
So then you take another point sort of halfway between that, say at the Tropic of
Cancer,
take an angle there, and it works out to be around 45 degrees, or just
45 miles.
45 degrees, which then puts the sun at around 3,000 miles high.
Right. So again,
and
there's no refraction when you're looking at the sun from the equator. There's no refraction going on, right? I mean, from the North Pole, there's no refraction because it doesn't.
Well,
everything you're looking at in your model has to deal with refraction.
I'd agree with you that the one at the North Pole could be out due to refraction or anything like that. But you take it where it's above 20 degrees in the sky, where there's minimal refraction effect, or it's all pretty well constant. Then the closer you get to that sun using the same method, the higher it gets in the sky. But you put those same measurements onto a globe, when those lines become parallel.
Onto an assumed globe. You still haven't proved the globe.
No, well, we've just proved that the light that the sun can't be close because it keeps moving all the time.
No, you didn't prove anything. You're assuming a globe. That's not how they figured out the distance of the sun. Do you want to know how they figured out the distance of the sun? Because they're not using your technique.
No. So I'm at the moment I'm trying to show it on a flat Earth. So, but
you can't triangulate the distance to an apparent sun. I'm sorry, you can't triangulate the distance to an apparent sun. And we have a video. It's like 45 minutes long, done by Dr. Zach. Tristan, you should send them the Dr. Zach video. It's in the app. But Decimal Z is the channel. Decimal Z. It's probably one of his newest videos. And it'll explain all of how ridiculous everything you're saying is. But do you want to know how they figured out the sun is 93 million miles away using math? Would you like to know? Because they didn't use your method.
Well, okay.
So one day, Venus transited the sun, okay? And they had somebody on the East Coast and the West Coast. I forget, maybe it was America. Maybe they did it somewhere else. And they filmed it and timed it, and it started at different times for each of them. Okay? Since Venus is about the same size as Earth, As it transited it, they did some perfectly good trigonometry, and they figured out the sun is 93 million miles away. Okay. What's wrong with that equation?
I don't know. What's wrong with that equation?
They assumed Venus is the size of Earth when Venus could be the size of a friggin' basketball, right?
No,
I don't know how big
weren't.
Venus is. They assumed Venus was the same size as Earth. So you can do math. Here's some math for you. You have $1 million in the bank.
They weren't using the size. They were just using the angles.
No, untrue. They're using the size. So here's some math for you. You have $1 million in the bank. I'm going to double it every day for 3 days. Tomorrow you have $2 million in the bank. The next day you have $4 million in the bank. The next day you have $8 million in the bank. You have $8 million in the bank. What's wrong with that equation?
No.
I assumed you had $1 million in the bank. Okay. You assume one thing, everything goes to shit. Everything. And that, so again, you're believing NASA, the proven liars, right? They're faking everything.
No, I don't listen to anything NASA has to say.
All right, that's good. We're in agreement there.
None of my research or anything like that. I have deliberately not involved.
Very good, Ben.
NASA.
Kudos to you there. So let me ask you a question. We're spinning at 1,000 miles an hour. Do you know how fast we're orbiting the sun?
Yeah.
66,600 miles an hour.
Well, we're spinning at
1,000 miles an hour at the equator.
Yeah. Yep.
We're orbiting at 66,000 miles. We're chasing the sun at 500,000 miles an hour, and the entire galaxy is moving sideways at 1,000,000 miles per hour or more.
Yeah.
Okay. How is it possible that we have monuments where we can look through a tiny little hole and see the North Star and it's never moved?
That's incorrect. It has moved.
That's another cool story, but you're gonna come up with the Thuban. We used to our North Star used to be Thuban, and in 40,000 years it'll be something else. But we happen to live in this amazing time where Polaris is right there. This was built 40 years ago. You look through this tiny little hole, and it's right there in the middle of the hole. It hasn't moved in 40 years. We're corkscrewing through space, traveling trillions of miles, and Polaris never moves.
But you got to remember, it's moving along with us as well.
So we're corkscrewing around the sun, and it's corkscrewing.
So you need to take everything into scale here. The size of our orbit around the sun compared to the distance between that star is like less than, in scale, say it was a mile away.
I get it.
A kilometre away, say. The orbit of the Earth around the sun was less than a millimetre.
I get it. So you're saying it's so far away that all of the movements of the Earth over the last 40 years and even longer are insignificant, and therefore it's like a tiny millimeter. The distances that they tell us, you can assume that. But let's talk about this. You know what the angular resolution limit of your eyesight is?
Yes.
Okay. So do you know what it is? Do you know what the actual angular resolution limit is?
Yeah. So that's why we can't actually see the size of the stars. We can only see the light coming from them.
So light travels forever, maintaining its brightness and maintaining its size.
Yeah, depending on how much light, its luminosity, how much it's emitting.
Do you know what the inverse square law of light is? Inverse square law of light is every time you double the distance to a light, it's 1/4 of the brightness.
Yeah.
Okay. So let's look at our sun. Our sun is 93 million miles away. It's 8 light minutes. If we made it 24 times farther, that's 3 light hours. Okay. And its size would be smaller than the resolution limits of our eyes at 3 light hours. Now,
so all it'll be is a dot of light in the sky. Yeah, that's
so at 3 light hours, it would look like a tiny star. I say you couldn't see it because its angular size would be too small. But
the angular size doesn't. That only determines actually seeing an object. That's not.
So,
It's like
so I
being
could
able
light
to
a
see a car
match.
down the road.
I could light a match and somebody 20 miles away could see it because even though its angular size is too small, the light will make it to them. Is that what you're telling me?
Well, no, because it's the light that it's putting out is not is not going to be good enough for you to see at with your normal eyes. But if you get a telescope or something like that, then yes, you will be able to see it.
So
Where
so
you're increasing
the
your
sun at 3 light hours, its
amount of
angular
light that's
size.
coming into the
So the
because
sun.
it's the amount of light that's coming into your eyes is what you see.
So
A
I'm going
little
to get
match,
into the amount of light
you're
coming
not
into our
going
eyes.
to.
The
What's
sun
that?
at 3 light hours is smaller than the angular resolution limit of our eyes. Polaris
Yeah.
is 46 times bigger than the sun, they tell us. So if we wanted to make that into scale, we could say, okay, 46 as like 2 days. So three, so if it was 6 light days away, it would be, its angular size would be too small for our eye to see. 6 light days away.
And that's why we only see a dot of light. We don't actually see the
I'm
ball.
with you. I'm with you.
Yeah.
6 light days away, it's too small and it's a tiny little dot. They tell us it's 433 light years away. Okay. And you're telling me that it gets smaller and smaller and smaller until it gets just the right size where it never gets any smaller. That's insanity. You're insane.
I've tried explaining this to him, but he wouldn't listen.
You're insane. You're insane.
Looks like there's no. I'll just go look into things too deeply.
Yeah.
By the sounds of it.
Why do flight paths from Sydney to Australia go all the way up into the northern hemisphere?
They don't, unless
they do.
They're
direct flights
from where?
From Sydney to Santiago.
No, there's a direct flight that goes from Perth to San Diego. I think it is.
It's Perth
There's
or Sydney, whatever.
Direct.
Same thing. It's the same problem. Yeah. It's the same problem. Direct flight. How come they go all the way in the northern hemisphere? How come they just don't scoot across the bottom of the ball?
Probably because there's not enough passengers just to have a direct flight. So
incorrect. Direct flight, nonstop direct flight, nonstop direct flight. Nonstop direct flight. Why don't they just scoot across the bottom of the ball like that?
So which flight are we talking about?
I'm talking Australia, whether it's Perth or Sydney to Santiago. This is showing Buenos Aires. I'm trying to find my flight map. Here it is. So going from Santiago to Sydney, they go all the way up here across the United States and all the way back down. And to make it worse, when they go to Perth, this is Perth over here, right? They go all the way up here. They go all the way over to Europe and Dubai and then down. Why do they do that? The answer is that no, direct flight. This is the path. They go up here, across Europe, Dubai, Perth.
Whoops.
Straight line. It's a straight line if you're looking at what I'm showing you. It's a straight line over the flat Earth plane.
I'm just trying to find the flight path. What was it? From Sydney
to Santiago.
I've done all this, Ben. I've sat there for 3 hours and watched the flight radar. There was nothing in the southern hemisphere.
Yeah, there's nothing. Ben, look at this. Instead of looking online for something that we've already looked up, take a look at your screen, all right? Because I'm running out of time. This is a flight from Buenos Aires to Perth. This is what Flight Aware. Are you watching here or are you looking at something else?
No, sorry. I'm just.
All right. Listen, just pay attention because we're running out of time. Buenos Aires to Perth. This is what Flight Aware says the route should be. But we don't want to disturb the penguins, so we fly around. That would be the shortest path. But that's not the path that they take. The path that they take is here. Buenos Aires to either Miami or Chicago, then California, then Sydney, and then Perth. It takes 26 hours, okay? Or they go to Europe, to Singapore, and to Perth, all right? So Max Egan, who hates flat Earth, he was taking a flight from Santiago to Sydney, I believe. And he So we did a live stream to prove that the flight exists, because a lot of people didn't even believe there was a direct flight, because it was very sketchy at that time. And we live streamed him getting on the plane taking off. We lost connection. We followed the plane the entire time. We stayed online for 14 hours, and then he landed. He jumped back into the hangout, and we proved that's what he did. But he took compass readings the whole way, and the compass readings were quite interesting, because he thought he was going to be going south and then southwest to Australia. And that's what they showed him on the seat back on the map. But that's not what his compass was showing. So he had a whole bunch of readings of northwest and then west and then southwest. And when we drew a straight line from from Santiago to Sydney, and we looked, all of these green lines are northwest. This purple line here is west, and these yellow lines are west, southwest, west, southwest, and then south. And that's exactly what his map showed. These are the directions that it went, and that's exactly how it works. If you look,
So
the compass always points towards the center, and it's only going west for a split second, and then it's going southwest and south. That's what his compass showed. That's the plane. But on the plane, they showed him doing that southern loop, right? So it's all lies, all run by NASA.
What plane was it on?
That was Qantas flight 9. I forget the flight. It's a 2-digit number. But we live streamed the entire thing, so there's no questioning it whatsoever. We proved that he did it. He showed the compass readings, and the compass shows the flat Earth map, the flat Earth route. Interesting, right?
It's interesting how that's the only one.
Interesting. Thank God.
All the others that you see.
What do you see?
Don't show it that way.
Well, they don't show it that way. None of them show it this way, but this is the way that they go, and we proved it. Nobody has gone from Santiago to Australia going over Antarctica. Why is that? Why has nobody circumnavigated the Earth south?
But they have.
Nobody has, ever. So look, this is why they can't. Watch this.
How do you
one
know
thing at a time. So check this out. At the center of the flat Earth is the magnetic center, and I'm pushing this compass dead west. But I have to keep turning, because west is a circle. This compass needle has to point towards the center. So west is a circle. This does not prove the Earth is flat, because it's the same thing on a globe. I'm pushing it dead east. East is a circle on a flat Earth and a globe Earth. Okay. As I have to keep correcting to the east. Now, if I want to dead reckon dead west, I'm going to follow dead west. I'm not going to correct. The second I start moving, I'm going south. Bam, I'm going south. South is every direction away from the center. Every straight line goes south. Nobody has ever gone south and popped up on the other side of the world. It's never been done, right? You can go here, north, 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 south, 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 and you keep going. But nobody's ever gone south. Every one of these lines is heading south if you're moving from the center outwards, and you don't come back. So if you're going north,
there's plenty of people that have navigated
nobody's gone around Antarctica. Nobody.
So all the ones on that you can look up are all false. Is that what you're saying?
Let's take a look, and then you tell me. So this is the world record for southern circumnavigation. So they started up here in the north. Pay attention. You got to pay attention if I'm going to explain this. Then we went over to Alaska. Then we went to California. Then we went down here to these islands. Here, so I think they stopped in Hawaii. Then they went to Santiago. Then they went to the South Pole, reportedly. And then they said because the weather was so bad, they turned around and they came back up to Brazil and back up. And they're like, okay, well, they're not going to get the world record. Well, Guinness Book gave them the world record for southern circumnavigation. This is what that really looks like. This is all he did. He went out here, he touched the goalpost, and he turned around and came back, and he got the record for southern circumnavigation. So this is the world record for the first southern circumnavigation. Does that make any sense to you?
They didn't do anything.
They didn't do anything. They went in a circle, right? Captain Cook was the last person. You know what? If you want to prove, here's the easiest way to prove the Earth is a globe. Easiest way. 13,000 miles is around Antarctica. Get two planes or two boats and have them go in opposite directions, keeping the shoreline in route. And two planes would be easy. You can do it in a day. And they would 7,000 miles later, they'd meet at the other sides, right? But nobody has ever done it. One, it's not allowed. Two, no one's ever done it. And the last person to try to sail around it was Captain Cook. It took him 3.5 years, and he went over 60,000 miles. Ben, look, 60,000 miles. And was something that should have been 13,000. Okay. You can't circumnavigate something on the bottom of a ball when it's really the outside of the world pond. Ben, you're clinging to your ball. You're clinging to it like a little child.
No,
okay?
I can just see.
I'm going to take him my shirt. Right.
Yeah, it's
Ben,
it's still the same. It's only just there's no actual. Yeah, it's all. Oh, yeah, it must work this way, or it has to work this way to fit on a.
Nobody has circumnavigated the South Pole. No one's ever done it. No one's crossed Antarctica and come up on the other side. No one's ever done it. They've all failed. And then if you look, like Ben O'Brien or whatever his name was, he went like from here. He went here. Then he went like over here. Then he went over here, and then he was picked up, and then went over to Africa or something like that. And they called that crossing Antarctica. No, that's not crossing Antarctica. That's skimming the shoreline of Antarctica, right? But then they write these stories. Oh, he did it by himself, and he went with no dogs and carried a 500-pound sled up ice. It's nonsense. It's all nonsense that you're believing. Nonsense. And you can't say, well, it's there's no proof. There's no proof of the globe. There's tons of proof of flat Earth. This circumnavigation of Antarctica proves it. Okay. And that would be the easiest thing. Flight routes prove it.
Well, flight routes don't prove it for a start.
Flight routes 100% prove it. 100%. If you,
I was looking at some flight paths the other day.
Yeah, but you're looking at cartoons. You're telling you, as I just showed you on that Sydney flight, that's not the route that they went. Check this out. Taiwan to Los Angeles. Out here is Hawaii. This is the route that they tell you it goes. This is the route that they show you.
Well, it doesn't really go that. It actually curves up a bit when you put it on a globe. It'll actually curve up a bit.
Well,
when you put
they say the Great Circle Route kind of goes up like this. Okay, why would it go up like that when the straightest? No,
go up a little. It'll actually go up a bit.
You're saying that to go from here to here, you go like that versus that. That's a great circle route too. Look, it's a great circle route. It all depends on the angle of the ball. This is to confuse your mind, right? So there was an emergency landing that happened. There was an emergency. There was medical emergency on the plane. They had to land the plane. So if you're right here, where would you land? You'd land in Hawaii, or
well, actually, if you map it out on a globe.
This is mapped out on a globe.
No, that's a straight line on a disc. If you map it out on a globe, you'll see that
it's a curved line over the curve of the globe. If I rotated that globe up, you would see a curved line. You can't have a straight line on a globe. So you're looking down on a curve. Look, are my fingers curved?
Yeah. Look,
they're curved. There's your great circle route. Look, straight line. You're looking down, curved line. That's all.
So what was the flight again?
Taiwan to Los Angeles. But here, Ben, look, this is where they landed. They landed in Australia, in Alaska. Straight line, emergency, Alaska. Hawaii is all the way out here. Okay. That's not where they went. All flights coming from like Australia and everything go north of Hawaii. It makes no sense.
How do you spell Taiwan?
Cawain.
TAW.
There's actually videos that actually show 17 emergency landings, I think it is, Dave, that prove a flat Earth.
There's a video, there's a book, great coffee table book You can buy it on lulu.com or it's free online PDF, but I recommend getting the book, put it on your coffee table, and if anyone picks it up, they become a flat earther. It's awesome. It's worth it.
To buy a P1000.
Why can't I find Taiwan?
Well, P1000 doesn't prove anything because of refraction. You can zoom in and you can see Taiwan because of refraction, dude.
Dave, you talking to me?
Oh, WA.
All right, listen, I'm not going to stay here while you're looking up flight routes where they're showing you fictitious flight routes.
Yeah,
they're going to tell you, that makes no sense. That it makes absolutely no sense that you would say that the great circle route is nonsense. This is a circle.
I just want to see where it sits on an actual globe, because I know it's definitely not a straight line. It'll definitely curve up a bit. And
why would it curve upright? Why wouldn't you go on a globe from any point to any point? A straight line, and a straight line on a globe is a curved line. So there's your great curved line.
Is actually curved.
Hey, can I say something, Ben? I've actually done this, and I watched Dave 6 months ago grab a piece of string and go from Sydney to Santiago on a ball, then try and curve it up or down to see whether it goes shorter. It actually doesn't work.
Doesn't work at all. The great circle route is just confusion for your mind. It's
yeah. Anyway, I'll definitely look this one up and just see.
Yeah, I'm sure if you just Google it, they're going to go, "Yeah, the Earth is flat." You caught us.
No, I'm going to look up this. But actually, I'll write it down. Is it Taiwan to
LA?
I'll give him the emergency flight.
Here's Amelia Earhart's circumnavigation. She's the one that proved the Earth is round because she went east. This is pretty much east. She's going east. She stopped at all of these places, even the land out over, and that's it. It's a circle.
Yeah, well, that one can be done on both a globe and a flat.
I'll give you that. So seasons can only be done on a flat Earth, not on a globe Earth. Circumnavigation east and west can be done on both. I don't agree. Circumnavigation south can only be done on a globe Earth, and it's never been done. The plane routes make sense on a flat Earth. They make no sense on a globe Earth. Large bodies of water lay flat. We can see too far. There's tons of evidence that doesn't work on a globe, works perfectly, and the only thing you have is refraction and gravity, okay? I'm sorry, you are lost inside your ball world.
I suppose the biggest reason why I don't I find it hard to believe a flat model is because there's no math that backs up everything that you say.
Actually, all math backs everything up, I say, except when you look up in the sky.
It doesn't. I just proved it just before that it doesn't back up what you say.
Actually, it does. You didn't prove anything because you're looking in the sky. You're looking, and you're the one that claims refraction and everything. You're looking up in the sky, and you don't know what you're seeing because we believe that there's a dome up there. We believe that that space is liquid. Put that.
So how big is the dome?
I don't know.
See this.
I can't reach it, and neither can you. You can't tell me how. You can't even tell me the radius of the Earth. Here, this is what happens when you mix liquid and curve anything that's curved. So we're looking through a curved. The sky, I believe, is curved, and the way our eyes work, you add water. Watch what happens when you add water. Okay, you can't tell what direction things are facing. You can't even tell what they move. Now I'm going to move the glass and watch which way the arrow goes. Okay. So when we're looking at things in the sky, all bets are off. Stop looking at the lights in your ceiling to figure out the shape of your floor, okay? Because you don't know what shape things are in the ceiling. You have no idea. Like, you think the moon is round, right? Is this a sphere? Is that a sphere? Well, half a sphere. Is this one a sphere? Ben, is this one a sphere before she grabs it?
It's a disc.
It's a disc? Well, it's flat. Is this one a sphere? Is this one a sphere? Is that one a sphere? Ben, quick.
No, it's a disc.
It's a cup. All you can see is so what I'm saying is you don't know anything that you can't reach and measure yourself. You don't know anything. Okay.
But you put features on it, then you can soon tell whether it's a dome by the light shining off it.
Untrue. I just watched a video today by a guy that's a glober that does stuff with magnets, and he literally, I'm going to add it to my presentation. He made a thing, and it looked exactly like a crater on the moon with the shadow and everything, but there was no crater. It was just done with magnetism and radiation. It's insane. I can't wait until we break this down on one of the shows. But again, anything we see in the sky is off limits. NASA, who's in charge of everything that has to do with getting around this plane, are known liars, and I think we agree on that. I don't believe that this is going on in Australia right now.
That's us.
No.
I mean, I have to believe that this is what from my point of view, is happening in Australia right now. Upside down nonsense. Okay?
That's what I'm trying to say, Ben. This is what
but okay. We'll go on to that one then. Your senses. What do your senses tell you?
That I'm stationary and not moving whatsoever, right? When you're in an airplane,
you're confusing acceleration with velocity.
No, curving is acceleration. Okay, when anything that curves, that's acceleration. It's the same force, right? So we're spinning at 1,000 miles an hour. The rim velocity of 1,000 miles an hour would explode. You spin something at 1,000 miles an hour. We've actually proven it. We've done experiments where we prove it. Rim velocity, not rotation. It's rim velocity that matters. Okay. But
what's the rim velocity?
That's 1,000 miles an hour.
No. That's the speed. That's not the velocity. The velocity is only 0.38 newtons.
No, that's the arc speed.
Meters per.
So you said trust your senses. Do your senses show you what this lake is showing you? Do your senses tell you that?
No, I didn't say trust your senses. I said, what do your senses tell you?
My senses tell me that I'm perfectly stationary. That when I look up into the sky, the same stars repeat every year. That the same eclipses happen every 18 years. Okay.
Yes.
All of this stuff negates gravity, negates the heliocentric nonsense.
But it doesn't.
Yes, it does. So scientifically,
it needs gravity to be able to do it.
No, you need gravity for your fairy tale. So do you know what the three-body problem is? Now, there's a thing called the three-body problem. So you got your sun. That's a gas ball in a vacuum. That's a problem. Okay. You got a gas ball in a vacuum that has enough gravity to hold on to the Earth and Mercury and Venus and Mars and Jupiter. It's holding on to all of them. And they go around and none of their gravities affect each other. Just the sun's gravity holds on to them. But each planet has a whole bunch of moons. Let me finish. Each planet has a whole bunch of moons that their gravity only holds on to the moon. How come when the moon comes around the backside of the planet towards the sun doesn't speed it up and rip it away, or at least perturb its orbit a little bit? And how come it doesn't slow down when it goes away from the sun? Does the sun's gravity ignore the moon? Or the Earth's gravity negates the sun gravity. Is that what you're going to say?
So it's all to do with the distance between the moon and the Earth. So because the moon's closer to the Earth than what it is to the sun, the gravity from the Earth is always going to overcome the gravity from the sun.
Cool story, bro. Cool story. So let me explain what the three-body problem is. The three-body problem is this, that you can take the world's best supercomputer and you can put a sun ball in it. So this big, this much gravity, you got another planet, and you put it in orbit, and the computer simulation works flawlessly into infinity. It'll work like a perfect timepiece. Then you add either a moon or another planet into that system, and the entire thing goes into chaos mode. No computer program can make it repeat. No one can predict what it's going to do next. No computer.
Yeah, they can. They do it every day.
No, they can't. Three-body problem. Look it up. No, they can't. They can't.
Yeah.
No. They tell you what's going on in our solar system, and that's just because our solar system's a perfect timepiece and it doesn't use gravity. But if you do a gravitational model, they can't do three bodies. And there's 60 in our solar system, and our billions in our trillions in our galaxy. That's the main, they
they use all the different. They include all the different, the sun, the moon,
Ben, that's a story they're telling you that they can't model. They're telling you a story of a system that works perfectly. The eclipses repeat. Think about this. The idea of an eclipse of a distant sun and a closer moon that happen to line up in perfectly the same size, how come they repeat every 18 years? That's impossible. They would never repeat once, right? All of the motions, none of them change. None of them change.
Why wouldn't they repeat?
Because we're in a crazy beehive system. Why would they repeat? We're corkscrewing through a universe. How nothing.
Yes, but everything's consistent.
Oh my God, Ben. Listen, Ben, I think I can't take it anymore. I'm done. I'm done, man. Ben,
if you look at it,
Ben, you seem like a really nice guy, but you are so brainwashed. It's not even funny. It's ridiculous. Okay. Don't get my app. Don't watch the daily videos because it's not going to help. Okay. Every question that you have is answered in there, but you will not see the answer. Don't waste your time. Enjoy your spinning ball.
Can I just ask you one question?
Shoot.
Can you supply me the maths that proves all this?
We can see too far.
No, the maths. I'm not saying we can see too far. The maths to prove that we can do it.
Ben, it doesn't matter because if I showed you the maths don't prove anything. Maths describe whatever you want them to describe. We can show you that it describes that we're not living on a ball. Hey, Ben, we're done. Enjoy your ball, buddy.
So you're not going to show me the maths then?
I would sit here and pull up all the what maths? You want to see 8 inches per mile squared for the first, couple hundred miles?
So take a picture where we see too far. Show me why the refraction doesn't allow us to see this far. The reasons why.
We listen, Ben. We went over this. You claim refraction.
No,
if it was refraction, it would be blurry. It would be changing. We wouldn't be able to go across a lake and keep it in. We wouldn't be able to do a time lapse over 24 hours. You're throwing in. Listen, the only thing you have is refraction, gravity, and belief. Okay, you have no proof of the ball. Zero. How come there's not a picture of the globe? There's none.
There's thousands of pictures.
Oh my God! Really? Really?
And
there's not thousands of pictures.
You say they're all. Why don't we have an actual picture of a flat Earth?
Because you can't imagine you're in a room that's 20 miles wide with 10-foot high ceilings. Take a picture of the whole room. You can't do it because a couple miles away, the floor will merge with the ceiling and you won't be able to see any farther. You can't. We can't get up high enough. Maybe you can get up high enough, but we can't. These are the pictures of the Earth. NASA's 2 greatest pictures of the Earth. The United States, twice the size. This one, they admit, was made in Photoshop. This one is absolutely insane because if you look at it, I'd be able to fit 8.5 of these between what they say the diameter is. 8.5 doesn't even fit on this page. This is a painting. You're believing paintings. Okay? You're believing paintings.
Do you know how a globe affects a picture?
What?
The closer you are, the less that you see of it.
Yeah, of
course. Further away.
But here, this is showing you that there's 934 miles that we can actually verify by driving it. So 934 miles there. So you're telling me because I'm close enough, the Earth really goes out to here. Is that what you're telling me? That I'm so close to it. Okay. I'm so close. Look how friggin' far I am from it.
Take a beach ball.
Hey, Ben, you are so deep into this. You're never going to see flat Earth. I'm going to let you go, buddy.
No, tell me this. If you take a beach ball, then you take a photo up close to it where you can still get the whole thing in. You can even draw rings around it so you know.
And you won't see the edge. Correct. So it's possible that this one's close enough where maybe the edge is out here because it just wraps around. It's dropping away. Like we could see this curve, right? It might be out here. It's not out here. Okay. You can't say that, right? Dude, you are just making up excuses to protect your little ball.
I'm
Listen,
not making
I've
anything up.
popped your fucking
This is
ball. It's
all-
gone. It's on the floor. It's flat. Whether you're going to cry over it or just pretend it's still there, go ahead. Go ahead. All right. Dude, it's over. It's over. It's over. Ben, it was good talking to you. I got to go.
Dave,
Yeah.
Don't get my app. Don't get the app. Don't get it. Don't get it.
I'm buying it.
I've already
Don't
seen
buy it for him. He doesn't need it. Leave him in his spinning globe world. All right.
I'll a couple of your shirts, and I'm going to send one to him.
Do not wear my shirt. Do not wear my shirt. All right, Ben. You guys have a good time in the land out over. Hey, wait. Check this out. Ready? Tristan and Ben, point up right now. Point up. Point up. Point up. That's, point up. Up is that way. Down is down. Okay?
Yeah, anyway.
Up is up. Up is not down. Up is not, we're not looking like this. Everything is up is up, down is down. All right, guys. See ya.
Dave, thank you so much. Love
See you guys. Bye.
Bye.
The Flat Earth Sun and Moon Clock App, a dynamic new app to teach family and friends about where they actually live. The sky is a perfect clock. The sun measures the hours and days. The moon measures the weeks and months. The star constellations measure the seasons and years. 12/12 or 24-hour clock face, or go hands-free. The Flat Earth Sun, Moon, and Zodiac Clock App with new added features. World Time. See what time it is all around the flat Earth. A true Earth compass that shows true navigation across and around the flat Earth plane. Weather. Tap for detailed local weather information. Know what phase and where the moon is at all times. Watch the sun travel between the tropics for the seasons. Select an amazing background. Add your own or have the app change it to a new one automatically every time you use the app. Add a countdown to your next big date. Learn the truth about our world with the featured video of the day. Web button for additional flat Earth related features, from the mythical curve calculator all the way to Tartaria. While talking to friends, easily pull up pictures that expose the globe lie and shine light on the flat Earth truth. Video playlists in different languages. See the real trade winds circling the flat Earth. And clean screen features. Simply click off the items you don't wish to see. The Flat Earth Sun, Moon, and Zodiac Clock app is the best tool to show your friends and strangers how our flat Earth actually works.